do know I'm summarizing the ones that there's already a video of an AP classroom, right?
Oh, so there's 2 titration curve videos?
Really 4 different types, I guess, even though 2 of them they're kind of similar. They just like flip.
I see.
So we're first going to do the curves of the type of titration we just did the math for. Guys, I do need it quiet. In a titration curve, we're basically going to graph pH in the flask on the y-axis. And we're going to graph volume of titrant. Titrant is what? Burette or flask? Burette. That's going to be on the x-axis. So when I say strong acid, strong base, I mean strong acids in the flask, strong bases in the burette. That being said, is the pH going to start high or low if it's a strong acid in the flask? It's going to start low. And this type of curve, the pH doesn't change very fast as we add strong base. So it's going to be pretty flat. I didn't draw that very good, I sucked. Kind of looks something like that. And I probably didn't make it flat enough. Let's make it a little flatter. All right, there, I'm happier with that. Now, no matter what type of curve it is, you're always going to see a steep portion. And in the center of that steep portion is always going to be our equivalence point. That is probably the most important thing you need to know about any titration curve is where the equivalence point's going to be. Always in the center of the steep portion. Now, if you were asked to sketch one, which occasionally they have you do it on the AP test, certainly not every year, the most important thing, Madison, you said you couldn't draw them, so listen. The most important thing is to have the middle part of that steep part at the right pH. So with a strong acid, strong base, what did we say the pH was at the equivalence point? 7. So I have to make sure that I draw my curve such that the middle of that steep portion is at pH 7. The most important thing you need when you're drawing a curve. And again, you may not have to draw a curve. Now, why is the pH low here? If you think about the RICF table that we just did, this portion of the curve is where we have excess acid. And then past the equivalence point, we have excess hydroxide. So conceptually, we need to understand what keeps pH low in this portion, what keeps pH high in this portion, and we've got to understand that the pH at the equivalence point is 7. Any questions on that? No. Now, what if we put a base in the flask and an acid in the burette? How's that going to change this curve? It's going to flip. Oh crap, I forgot to talk about calcium hydroxide. I forgot to talk about calcium hydroxide when I did the math. Just what? If I remember, I will.
Oh my God.
So, how's this going to look different if we put the base in the flask? It's going to see same general shape, but now it's going to start high and then go low, so it's going to kind of flip like that. So it's going to look more like, and then boom, something like that. Changes? If I put a base in the flask. So this would be strong base in the flask. And strong acid in the burette. And again, pH at the equivalence point is going to be what?
7.
All right, that's pretty much it for strong acid, strong base, strong acid. I'll give people a chance to finish copying, then I'll do the other 2 types. The ones with much more complex math that we are going to cut out. do a little bit of math with those titrations.
The AP video complicated that like.
Yeah,
So
yeah,
much.
I'm telling Miss Thatcher, she was.
I just can't
going
I
home.
can't.
Like, what's the point of the excess? Like, what is like?
Because the way they ask questions, they could ask you questions that make you explain why it's high pH past the equivalence point. So you need to understand it's because hydroxide's in excess. I mean, and if you look at the RICF table, you should be able to kind of remember what you were explaining. Remember how with the last problem in point E, now OH was the one that was left over and the acid hit 0.
Oh. Okay.
That's what I mean by excess, is the one that's left
Okay.
at the end.
Oh. So I'm guessing.
Does that make sense?
When they graph it, is it with molarity?
It's pH. This is
Oh.
pH, this is the volume added from the burette. And it's showing how the pH is changing.
Okay.
Can I erase?
Yes.
All right, let's do the fun ones. All right, so let's do weak acid, strong base. And these are a little more complicated. We got a few more things we have to talk about. So weak acids in the flask, strong acids in the burette.
Wait, weak acid strong? Oh,
Weak
strong
acids
base.
in the flask. So if we were doing math, we'd be doing a Rice table instead of negative log. So x-axis is going to be volume of titrant. Now, if we have a weak acid in the flask instead of a strong acid, do you think the pH is going to be as low at the beginning? No. pH is going to generally be a little higher at the starting, and it's not going to be as flat. And again, I kind of suck at drawing these, but I'm going to do the best I can. So not as flat, it might look more like that. And this portion where it shoots up is not as big. So it's not as flat, and the steep portion is smaller compared to the type we just looked at. The other type looked something more like this is more. So subtle differences. Now, even if you suck at drawing like I do, the big super important thing is, let's talk about pH at the equivalence point. First off, where's the equivalence point going to be? Right there in the middle. So that's my equivalence point, and I'm going to kind of do a hypothetical RICF table. So let's just take a weak acid. Let's say we're doing HF plus OH minus. What are my products? H2O and F minus. And I'm telling you now, I'm making up the number 5. I'm trying to demonstrate a point. At the equivalence point, what would the number of hydroxide be? It would be 5. So these both hit 0. But is it going to be pH 7? Because what do I have? When these get wiped out, I have F minus, which is not neutral. What is it? It's a weak base. So what's the pH going to be? Above 7. So you've got to understand the differences, pH above 7, and you have to understand why. Because at the equivalence point with this type of titration, we will have a weak base. Because the conjugate base of a weak acid is a weak base, pH is above 7. Does that make sense?
Mm-hmm.
Now, this region is called the buffering zone. And I'm going to talk about why that is. So let's pick any point prior to the equivalence point. Let's just say 2 moles of hydroxide. So which one's hitting 0?
Wait,
All right, hold up. Huh? Okay, because at the equivalence point, do you agree these are both 0? We're left with a weak base. F minus is not neutral because it's the conjugate of a weak acid, not the conjugate of a strong acid. Remember, any negative charge is a weak base unless it's the conjugate of a strong acid. So we have a weak base present in water that's going to be pH above 7.
Hmm.
Does that make sense? I made it up. We can take any number. These two are both 0 at the equivalence point, and we're going to have a weak base present. Because at the equivalence point, these are all the same. I just gave you a number so you can visualize.
Okay.
All right? Now, so I'm demonstrating why we call this the buffering zone. Guys, I need it quiet. Eric, put your phone away. So, prior to the equivalence point, we can pick any number for hydroxide. I'll just take 1. So this is hitting 0. So now what do we have present? We have HF and we have F minus. What type of a pair is this? Conjugate pair. So this is a buffer solution because remember, buffers have both parts of a conjugate pair. If we were doing the math, we would do Henderson-Hasselbalch equation here. So here we have HA and A minus both present. That's why it's called the buffering zone, because we have a conjugate pair present in the solution. Now, the midpoint we need to talk about. Midpoint we said is what? Halfway to equivalence.
Wait, you said it's called a buffer pair or buffer conjugate?
This is called the buffering zone because at all points in this region, we're going to have both parts of a conjugate pair present. And that's what a buffer is. It has both parts of a conjugate pair present. Now, at the midpoint, so what would my moles of hydroxide be at the midpoint? 2.5. So this is 0. If we think about the Henderson-Hasselbalch equation, remember where we do log of base over acid? We're doing 2.5 over 2.5. So HA equals A minus, and pH is going to equal the pKa. And that's very important. College Board loves to test that. So I'm going to show you an example of the type of question they ask just about every single year on the AP test.
Wait.
I have a quick little question.
Yes.
Do you need to know why pH was pKa? Like
I will show you why. I will show you why. Okay. So using our numbers up here, do you agree that the Henderson-Hasselbalch equation is pH equals pKa plus log of base over acid, right?
I do.
So in this case, we're going to get pKa plus log of 2.5 over 2.5. Log of 1 is 0. Since this is 0, pH is equal to pKa because this is 0. And at the midpoint, they're always equal to each other. So you always get a log of 1, which is 0. That's why.
Okay.
Does it make sense?
Yes.
Okay.